In this video, I'm going to show how to use the spectral method to, to compute the solution of a couple Cahn-Hilliard equations in multiple dimensions. And in particular, I'm going to use a semi-implicit method. Now, previously, in another video, I also used the spectral method, but I did it in a different way. So what I did is using a library of ODE solvers to solve the system of ordinary differential equations that results from applying Fourier transform in x and in y to the original set of equations. Now, this time I'm going to do something different. I'm going to use Python, and instead of using a library of ODE solvers, I'm going to use a semi-implicit discretization. And I want to show first the details. So this thing here is the system of coupled equations. B1 and B2 are the coupling constants. The sigma is necessary for the phase separation in the copolymer. This tau u, tau b here are the speeding factors. And after I apply Fourier transform in x and in y to this system of equations, I obtain the following two expressions. Here the quantities in red and in blue color are the wave numbers. And what I'm going to do now is using a semi-implicit discretization as is shown here. So what I have here is I choose the value of the u variable for the next time step for the term corresponding to the fourth order derivative. For the remaining terms, I am just going to use the value of u at the present time step. Similarly, for b, at the next time step, I'm going to choose the term corresponding to the fourth order derivative, and for the remaining terms, I'm going to choose the value of u and b at the present time step. Now, how to solve this expression? Well, first I need to collect the terms to solve each one of these expressions for u, n plus 1, and for b, n plus 1. I'm going to collect the terms, put everything together, and what I get is the following. This one is for u, and the corresponding solution for b is the following one, this one here. So how to solve this? This is actually very simple to do. What I'm going to do is first I start from an initial condition for u and b. I'm going to choose random initial condition, and then before computing the Fourier transform, first I need to compute several products. This one here, and another one for the product of u and b. And then after I get this product, then I am ready to compute my Fourier transform in u and b. Similarly for the rest of the terms. And with that, I complete the first iteration. Once I get the first iteration, then I just take the result, put it as initial condition for the following iteration, and I continue this process for several thousand time steps. And after I finish, then I'm just going to take the inverse Fourier transform and plot the results. And that's what I'm going to do in the next part of this video. In this part of the video, I'm going to explain how to use Python to compute the solution of this expression here for u and for b. I already wrote the code, so I'm just going to explain. This is the function. So we are going to start using a random initial condition for u and for b. The random initial condition is generated here. I use a random distribution with some amplitude, some small amplitude, and center about some mean value. In particular, I'm going to use 0 as a mean value for u and for b. In here, in this part, I am just defining the wave numbers. This is very similar to what I did before with MATLAB. My domain has a period 2 pi. This is the spacement between nodes and the number of nodes, n, capital N. Now this is just a one-dimensional array of numbers. To convert this into a square domain, I use this function here, measure. And I am going to also need the square of the wave numbers to compute this k square and this k4 defined like that. So I need to compute this square and then the summation. That part is done here. I compute here the square of these wave numbers and then perform the summation. Once I have my initial condition, then I take the Fourier transform, and then I'm going to take this u hat and b hat and plug it into the time loop right there. And I also need some other quantities. For instance, to compute this part here, this is u cubed minus u. See, it's right there, u cubed minus u. Similarly for b, we need b cubed minus b. I also need this product here, b squared. B squared is necessary here, this part. I also need the product to compute this term here. I need the product of u and b. That product is right there. So I have u and b, and then I compute the product. I'm going to call it ub hat. So when I have all these terms, I'm going to construct my function for u hat. U hat is this, you see, you have u hat first, then dt k2, and then multiply by this df du. Df du is this part here. Is this part right there, minus dt k2, minus dt k2, and then right there, this part here. The remaining part is dt multiplied by b1, this term here, and then half b2 k2, k squared is this part here. This dt multiplied by b1, this term here, and then another term, half b2 k squared b squared. So the half b2 k2 b hat squared. And this is the lower part of the expression for u hat. This is 1 plus dt epsilon squared k to the fourth, this one here. So 1 epsilon dt k to the fourth. And we have a similar expression for b, but it's going to be a little bit more complicated because it involves this term with the sigma there. So the sigma is going to appear right there, sigma b hat. Sigma b hat. The mean value is 0 in this case. The lower part is similar to what I did before, 1 epsilon squared delta t divided by this speed factor k to the fourth, right there. dt tau b epsilon squared k2 squared. So by the way, in this case I'm using epsilon, u is equal to epsilon b. Alright, so once I compute u hat and b hat, at the end of the time step, I'm going to compute the inverse Fourier transform. I'm going to repeat this process for a number of times, and the final result, I'm going to plot it. So we are ready. I'm just going to run this code to see what happens. It takes a couple seconds. Alright, so that's it. This is u. You see, this is a region in red. Color is about close to +1. The region in the dark blue is close to -1. This one on the right hand side is the particle, is the microphase separation. This bright yellow is close to 1, this dark blue is close to -1. And by the way, this is with sigma equal to 0. If I compute the same thing for a larger value of sigma, then we expect microphase separation inside the particle. I'm going to run this code again with sigma equal to 20. And it takes a couple of seconds. I am running this on a laptop, so this code is quite fast. Okay, so once again we have the particle there, and then on the right hand side we are going to have the microphase separation with sigma larger than 0, so we have more layers here. Alright, so with this I conclude the explanation of the spectral method with a semi-implicit discretization to solve coupled Cahn-Hilliard equations in multiple dimensions.